All right, good morning. What we're going to do today is finish off the unit by looking at lesson 6.4, which ties solving equations that we learned about in the previous unit to working with identities that we've been working on in this unit. That will leave us tomorrow and Monday for unit review. I do have the unit review materials ready, so I will probably hand them out to you today and talk a little bit about the review today. And that means your unit exam is on Tuesday of next week. I'm planning a little quizzy tomorrow, like a 10-minute deal, dealing with identities and or what we're dealing with today. Okay, it's kind of, we're in the realm now of me expecting you to be able to do stuff with trig, whether it's solve an equation or simplify an identity. I'm not going to give you on a quiz a proof because it's too time consuming. Okay? There are more efficient ways for me to find out if you know what you're doing than dealing with a proof. Over the past couple of days, we've been working with proofs. I'm going to not spend the beginning of today's class going over any proofs. Instead, I would like to get into the final lesson and get that done and out of the way. And then certainly if you have more questions dealing with proofs, we have time after this lesson, we have time tomorrow, we have time Monday to go over any additional problems. So what we're looking at today is, it's called Identities and Equations in your textbook, section 6.4. And what it is solving trigonometric equations that you could not solve before you knew about identities. And will have picked up on this idea that I have in high school math many times throughout the semester, that it's always a good idea to take something that you are learning that's new and turn it into something that you knew how to solve yesterday, or last week, or in grade 11, or in grade 7. Right? This is a really good problem-solving strategy. You take something, you apply the most recent ideas that you have to it, and hopefully it turns into something simpler. All of these questions today are going to turn into equations that you are expected to know how to solve in the previous unit. And we're just going to be using identities to do that. Again, with all trigonometric equations, you're expected to be able to solve them as exact values or as approximate values. So if I give you this equation, example number 1, and it's the same as the proofs lesson in terms of me telling you there's a similar example in your textbook. You're asked to solve each equation here in example 1 for the domain of theta is between or equal to 0 and 2 pi. So for a full revolution, including the beginning and the end. And if I gave this to you in the last unit, you wouldn't know what to do. But if you look at this now, there's really only one thing you can do. And I'm glad to see that you guys are looking at your formula sheets because we're talking about identities here. On your formula sheet, sine of 2, I don't know what it is, theta, alpha, it doesn't matter. Sine of 2 times the rotation angle is 2 times sine of the rotation angle times cosine of the rotation angle. I suspect it's alpha on your formula sheet. Okay, thank you. So all we're going to do is make that replacement. This equation is going to go from sine of 2x minus cos of x equals 0 to 2 sine x cos x minus cos x is equal to 0. And as I started off my discussion today of what we're doing, here's evidence of what I was talking about. This has now turned into a Unit 3 question. I'm not claiming that everybody remembers without effort how to do this, but it is something we've learned before. In this particular case, what we can do is we can factor out a sine of x and be left with 2 cos of x, pardon me, factor out a cos of x and be left with 2 sine of x minus 1. And now we're kind of thinking math 20 here in terms of solving an equation. This is not quadratic. but it does have an equation where you have one factor multiplied by a second factor equaling 0. So now what happens is we end up with cos of x is equal to 0, and 2 sine of x minus 1 is equal to 0. And I know you might get tired of me saying this kind of thing, but it is now turned from an equation that we would be expected to solve near the end of Unit 3 to an equation that we knew how to solve near the beginning of Unit 3. And to be honest with you, as soon as we write this, it's turned into a Math 20-1 trig equation, except that we're dealing with radians and the unit circle, right? But this is something that you explored how to solve in Math 20. You would have used your calculator and talked about reference angles and that kind of thing. So now all we need to do is identify in this domain from 0 to 2 pi, first of all, not the angles, but the positions on the unit circle where cosine of a rotation is 0 and where sine of a rotation is 1 over 2. So when we take a look at that, cosine is 0. Once again, going back to Unit 3, this is the x-coordinate on the unit circle. I mean, you don't have to write that, but I'm pointing out that that's what we're doing. Because it's cosine, we're looking at the x-coordinate. The sine of x, or the sine of a rotation angle, is the y-coordinate on the unit circle. And it's never too late to review this kind of idea again. I hope that everybody knows that's the case. So when we look at that statement, where on the unit circle is the x-coordinate 0? Well, the x-coordinate is 0. Let me clean that up a bit. I'm not even going to draw a circle. The x-coordinate is 0 in this location and this location, right? There's no significance to the fact that I drew an x in a circle. I'm just marking off the locations. Where is the y-coordinate 1/2? Well, the y-coordinate is 1/2. I'll just draw an arc here so you get an idea of what I'm talking about. The y-coordinate is 1/2 here, and on the other side, here. You can draw a circle, you can draw part of a circle, you can visualize it in your head. Of course, if it's a written response, you should probably draw something. So what we're talking about here is the rotation angle to get to this position, to get to this position, to get to this position, and to get to that position. That's what we're talking about. We're talking about all 4 of those rotation angles to get to those 4 positions. So pi over 6 would be a solution. Pi over 2 would be a solution. 5 pi over 6 would be a solution. And 3 pi over 2 would be a solution. So x is equal to pi over 6, 5 pi over 6. Well, I'll put them in order. Pi over 6, pi over 2. Just make sure I'm writing that down right. Yep, 5 pi over 6 and 3 pi over 2. So again, not to belabor the point, but we went from an equation, what's typed out there in black, that you did not know how to do prior to today. As soon as you made that trigonometric substitution, you've turned it into an equation that you did know how to do before, so we solve it like we did before. Any questions with that example? This is the goal. You're taking identities and you're rewriting the equations into a simpler equation to solve. So for example, with b, we have 2 cos x plus 1 minus sine squared x is equal to 3. Can you confirm that's the equation you have written there? Typed out? Okay. So the issue here is this is an amalgamation, a mixture of cosines and sines. And it's much easier to solve a trigonometric equation if it's dealing with sines or cosines. Not always. This previous example had sines and cosines, but it was still solvable. This does not. So how can we, this is not. It's not solvable in its current form. So what can we do here? Well, I'll ask you, does anybody have an idea of what we can do to change this into an equation which we could solve? Maria?
Change 1 minus sine squared x to cos squared x.
Right. Change the sine squared x's to cos squared x's. Now, what's interesting here is this is like standing out there. It's like it's waving a flag at you, right? It actually says 1 minus sine squared. I want to come back to that a little bit later because it's not always going to look that way. Okay, it will not always look that way. I've given you this question this way so that hopefully you recognize there is 1 minus sine squared of x, and we can write that as cos squared of x. I hope everybody understands that. Sine squared x plus cos squared x equals 1, and this that I've written on the right-hand side of the screen is just a variation of that identity. So I can put in here cos squared of x. And now I have 2 cosine x plus cos squared of x equals 3. And it's a trigonometric equation now that's quadratic that we learned how to solve in the previous unit. So I can write this as cos squared of x plus 2 cos of x. And in Math 20, you learn that when you solve any quadratic equation, you always zero the equation. So I subtract 3 from both sides. Now, is that factorable? Are there two numbers? And I'm asking this question because the coefficient of the quadratic term is 1. There's no complex trial and error decomposition method involved here. You're just saying, are there two numbers that multiply to give -3 and add to give +2? The answer is yes, +2 and -1. So we can factor this into cos of x plus 3 cos of x minus 1. Don't forget to write equals 0. And just verify this. I'm asking you personally to verify this on your own. That if you FOIL this out, if you multiply those two binomials together, do you get the cos squared x plus 2 cos x minus 3? And the answer is yes, you do. Okay? So that means that we have cos of x plus 3 equals 0, and we have cos of x minus 1 equals 0. I'm writing that because if it were a written response, I think you should probably write that. I think most of us just working in our day-to-day math life would probably have just gone immediately to cos of x equals -3 and cos of x equals 1. Cos of x cannot be -3. There are a number of ways for you to justify why that's not possible. One of the ways is to say that I know the graph of y equals cos of x oscillates up and down with a range from -1 to 1, so cosine of x will never be down at -3. Another way is to say that since cosine of x is the x coordinate on the unit circle, and the unit circle goes from -1 to 1 for x, then you will never get an x coordinate of -3. However, for cosine of x equals 1, this is the only location on the unit circle where cosine is equal to 1. Because again, cosine is the x coordinate. And this point on the unit circle is at 1, 0. So that's the position. That's not an answer to the question. That's not an angle. It's a position. Now, how can we rotate to get to that position within the confines of our domain from 0 to 2 pi? well, 0 is already there, but we can rotate around 2 pi. And we include both 0 and 2 pi because of those equal to parts of the inequality statements. So what are we getting here? We're getting x is equal to 0 and 2 pi. And that's it. Any questions with B? That's a classic kind of substitution, by the way, of getting rid of a squared using the Pythagorean theorem. But let me throw something else your way here. If I go back to the original question, I hope you can conceive of a situation. I don't want to get rid of this, so I'll just clone it. I hope that you can conceive of a situation where, and I'm not going to make up an entire equation, but maybe where you have the following. And let's not worry about the solutions to this, or if they exist. In fact, I'm just going to say there's some other stuff here that's equal to, okay? How do you deal with this? Because in the original question, as Maria pointed out, and we noticed, there's 1 minus sine squared of x just standing right out there, staring at you. So what do you do here? Well, there is an option. And again, we're not solving this. Okay? How many of you would immediately say then that this is 2 cos x plus 4 plus 1 minus sine squared x? You could do that, I suppose, right? And then put in cos squared x here. Are you with me on that? Okay. But what if there isn't even a number there? What if it's just this? 2 cos x minus sine squared x. Well, then what you're going to do is you're going to take this identity. Well, there are other options, but when you take the Pythagorean identity and rearrange it for sine squared of x, it's 1 minus cos squared of x. So you can put in here 1 minus cos squared of x. So you would get 2 cosine x minus 1 minus cos squared of x, of course remembering to put it in brackets. So there's lots of ways. I mean, what you're doing is you're using your algebraic skills of substitution here. And if you happen to see, oh, 1 minus sine squared, oh, okay, you can put in cos squared. If you don't, you know what I'm saying? If you don't, you have to find a way to make it work. You have to find a way to use that identity to help you. All right, let's try another one. Sine squared of x equals 1/2 tan x cos x for a domain from and including 0 degrees up to but not including 360. The question I have for you here is just by a nod of the head or a wave of the hand, how many of you have gotten to the point where when you see tangent x cos x, you know it's sine x? Right? Because tangent is sine over cosine. Well, I think that's the smart move here. Given that the left-hand side of the equation has sines, if we were to rewrite this, right-hand side is 1/2 times sine x over cos x times cos x. Then we can eliminate the cos x's from the equation and have sine squared x equals 1/2 sine x. And that's certainly easier to work with. From a not math 30, not math 20, not trigonometry, from a math standpoint, I think getting rid of that fraction is the most important thing to do right now. Whether it's trigonometric, logarithmic, which you don't know about yet, algebraic, it doesn't matter. Rational, if I multiply both sides by 2, I get that. This is a quadratic equation, so it must be zeroed. And I'm really stressing that because you can make a fatal mistake here that I'll talk about in a minute. So I'm going to take 2 sine squared x and subtract sine x, and now I set it equal to 0. I can factor a sine x out. You probably don't remember, but when we first learned about quadratic trig equations, I went through a case where we have a quadratic, linear, and constant term. I went through a case where we have a quadratic and just the constant. And I went through a case where you have quadratic and linear, and this is how you do it. You factor out the common factor. And you're left with 2 sine x minus 1. Well, I would say not only have we made it simpler, we've made it simple. We're in the territory of taking candy away from a tired baby. It should be really easy. If everybody is looking at this, everybody should be saying, I can do this. This is sine of x is equal to 0. This is 2 sine x minus 1 equals 0. So that becomes sine x equals a half. Don't forget that because it's sine, we're looking for the y coordinate on the unit circle, obviously, and you would probably write on the unit circle if you were doing this for a written question. So where on the unit circle is the y coordinate equal to 0? Well, the y coordinate is equal to 0 at this location and this location, right? Those are not angles, they're positions, they're locations. Where is sine equal to 1/2? Here and here. So now we can answer the question. Am I correct in remembering that we're including 0, but not 360? Okay, so 0 degrees works. 0 degrees is right here at this location. This is 30 degrees. 5 pi over 6, which is this location, is 150 degrees and 180 degrees. Now, if you stopped there, you would get the right answer, okay? And it is correct. However, because of this, cosine of x is not allowed to be 0. There's a non-permissible value in this equation. So where is cosine 0? I'm not saying this is a solution to the equation. I'm just saying we're finding out the value that x would not be allowed to be. Cosine is 0 at the top and the bottom of the unit circle. So this is telling us that x is not allowed to be 90 degrees plus multiples of 180 degrees. Right? If you look at the unit circle, cosine of 90 degrees is 0. Cosine of 270 is 0. But you can't be at those positions then because cosine would be 0 and you would be dividing by 0. So my question to you is this. We did all this work to get these 4 angles. Are any of these 4 angles non-permissible? The answer is no. They're all allowed. But you have to watch out for that. Number 3, cos 2 theta equals cos theta, and we want a general solution this time. Well, you have options. There's options. For cos of 2 theta, I can substitute in cos squared theta minus sine squared theta. And I can use that with more work to get to the answer. Okay? Or I could put in for cos 2 theta 1 minus 2 sine squared theta. I'm looking in my head anyway, figuratively speaking, at a formula sheet. You're looking at your formula sheet in front of you. Or you've memorized these accidentally. And if I do that, if I put in 1 minus 2 sine squared theta for cos 2 theta and do more work, I can get to the answer. Or I could put in 2 cos squared theta minus 1 for cos 2 theta and with less work get to the answer. And I hope you see that the third option is the best option. Because if I use the first option, I will create an equation that contains sines and cosines. And you can get rid of the sines if you like with the other Pythagorean identity that we've talked about today. The same would be true using the middle option. But using the third option is the wisest move. This becomes 2 cos squared theta minus 1 equals cos theta. And now this is I can't believe I'm saying this because we called this a complex trigonometric equation earlier in the year. I'm saying this is a pretty simple quadratic equation to solve, right? You zero the equation, 2 cosine squared of theta minus cosine of theta minus 1 equals 0. Factor and solve. And again, I don't mean to minimize the skill that's required to finish this question, but as far as quadratic equations go with trig, this one's pretty tame. In fact, I don't know if you recognize this. This 2, 1, 1 for the coefficients is popular. It's very often we have that. 2 cos theta and cos theta. It's a trial and error situation, but you don't have many options here. You've got to put 2 cos theta and cos theta. For the 1 at the end, you have to have a 1 in each of these positions, and it's a matter of saying where do you put positive 1 and where do you put negative 1. You have to have one of these 1s as positive and 1 as negative because they multiply to give that negative 1. A little bit of thought. I believe that's factored correctly. Don't forget equals 0. It may seem like a trivial thing, but it is an equation. That means that cos of theta is equal to negative 1 over 2, and cos of theta is equal to 1. Admittedly, I didn't write the intermediate step there. I could write 2 cos theta plus 1 equals 0 and go from there, but you know, I think we've warmed up enough today to just handle that. Where on the unit circle is the cosine equal to 1? Here. Again, this thing that I keep writing is that important. I'm not writing it because I just want to spend more time writing. It's that important. That this is an x coordinate on the unit circle, and this is an x coordinate on the unit circle. So the x coordinate on the unit circle is 1 at that position I've marked. It's negative 1/2. I mean, it might help for you to draw a circle. Don't forget what I've said. You can have a cup of coffee in the exam room and in your exam time and just draw a circle with that. If you're not that good with drawing circles, you can use a loonie. Negative 1/2 is here and here for the x coordinate. So that means, and I'll remind you of something, when you're looking for a general solution, my advice is just go for 2 pi and then start adding multiples of 2 pi. So if I just list these off, going from 0 to 2 pi, I would say 0, 2 pi over 3, and 4 pi over 3. Right, 0, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. My circle's a little monstrous, but that's okay. And then what you could do, this that I'm going to write is a legitimate answer to this question. You could say that theta is equal to multiples of 2 pi to cover that. 2 pi over 3 plus multiples of 2 pi to cover this, and 4 pi over 3 plus multiples of 2 pi to cover this, where n is an element of the integer number set. And if this were a written response, that would be fine. But I think it's also important that you recognize, despite my very lousy circle, these are all 120 degrees away from each other. So I'm going to clean that up, and I have better luck drawing circles if I draw them first and then put the axis on there. So we're talking about this location, and this location. They are all 120 degrees away from each other, consecutively speaking. 0, 120, 240, 360. So you can write all of this, or you can say theta equals multiples of 2 pi over 3. And that will give you the 4 pi over 3, the 0 pi over 3, the 6 pi over 3, etc. Okay, so I'll pause there. Does anybody have any questions about the work with that one? Maybe a little lesson to be learned, and sometimes I get moving too fast and I don't follow my own advice. Draw a nice circle. Try to draw it nicer. I do want to go back to example number 2, because there is something that I wanted to talk about here. And I had mentioned that there is a mistake that students will make here, and it's a fatal mistake, and you cannot do it. Well, you can do it if you want, but it will be wrong. They look at this right here, this 2 sine squared x equals sine x, and they go, well, let me do this. They divide both sides by sine x. And what they get is 2 sine x equals 1, so sine x equals 1/2. And if you look at your work for this question, we had the following 4 positions for answers. We had pi over 6 and 5 pi over 6, which will give you sine equals 1/2, but this person who canceled the sine x from both sides does not get these 2 solutions at the top. You can never divide out a variable. What this person has done is the equivalent, everybody, of this. And as soon as I show you this, you'll go, well, of course, I would never do that. Let's say you have the following quadratic equation. And you factor it. We know there are 2 solutions, right? Well, what that person did is the equivalent of what I'm about to do. It looks a little bit different, but it's the equivalent. You can't just divide out a factor that contains a variable. You have to zero quadratic expressions in polynomial equations. All right, we have one last example to do. Number 4. 3 cos x plus 2 equals 5 secant of x, and we want a general solution in radians. What should we do? And most of the time with these equations, the issue is that you've got different types of trig ratios, and we don't want different types. There are exceptions. But, you know, in this previous question, that we were just talking about, we had sines and tangents and cosines, and we got it so that it was all sines. In the one before, we had a mixture of sines and cosines, and we got it so it was all cosines. So is there a path we can follow here to get it all the same type of trig ratio? The reciprocal identity. And we could change the cosine to 1 over secant, but I think that's asking for trouble. Let's change the secant to 1 over cosine. So now I have 3 cosine of x plus 2. And by the way, I just mentioned this because every now and then my brain does this. I hope it's obvious that this 3 cos x plus 2 is not this, right? Okay. Equals 5 over cos x. I mean, I could have written equals 5 times 1 over cosine of x. It doesn't really matter, I suppose. So now you're looking at that equation. Well, that's just a sliver better. It's just a little bit better. But again, not talking about trig or math 30 or math 20 or anything, just talking about math. Fractions are things we would rather not work with. So I am allowed to multiply both sides of this equation by cosine of x. And when I do that, on the left side, I'm going to get 3 cos squared of x plus 2 cos x. And on the right side, I'm going to get 5. Now I can move it over. So now we're in more familiar territory. Now we're back in Unit 3. And I suppose I could argue that as soon as we rewrote secant as 1 over cos, we were back in Unit 3. This becomes 3 cos squared of x plus 2 cos x minus 5 equals 0. Not a very familiar combination of coefficients for a quadratic equation. So is it factorable? I don't know. It might not be. Prior to this point in the course, I would probably say, with trig, we would never have to use the quadratic formula. Everything's on the table now. However, let's find out if it's factorable or not. Remember, b squared minus 4ac will be a perfect square if the quadratic expression is factorable. So that would be 2 squared minus 4 times 3 times negative 5. And I believe that's 64, which makes this factorable. But is anybody else in agreement that that's equal to 64? I'll give you a minute. It is. Okay. So it is factorable. Now I know the pursuit that I'm undertaking has a destination. I'm not just spinning my wheels getting frustrated. It must be 3 cos x and cos x. There are no other options. And the negative 5 must be 5 and 1. And if you look up here, if you say the negative 5, forgetting about negative, the 5 must be 5 and 1. As soon as, if you do this, as soon as you start writing the 5 here, your brain should be saying, wait a minute, that's going to give me 15 cos x's if I were to multiply it out. And I don't think I can turn that 15 into 2 cos x. So the 5 must be over here. The 1 must be here. It's a matter of playing around with the signs now. By signs, I mean pluses and minuses. My outer is 3 cos x. My inner is 5 cos x. And I need positive 2 cos x, which means the 3 cos x must be negative. And now I have to ask myself, where did I get the 3 cos x from? Oh, from the 1 and the 3 cos x, which means the 1 is negative and the 5 is positive. That means that 3 cos x plus 5 equals 0. And cos x minus 1 equals 0. This question, or this equation, turns into one that's very simple. The solution is simple because the left-hand part that I've got here for the linear equation 3 cos x plus 5 equals 0 becomes cos x equals negative 5/3. And it can't equal negative 5/3 because negative 5/3 is outside of the range of values that cosine of x has. That would require some level of explanation on a written response. This equation, the other linear equation, the other half of the quadratic is cos x equals 1. That's the solution. You know, again, cosine of x is the x-coordinate because it's cosine. The x-coordinate is 1 in one and only one location, and it's there. Just to polish this off, we were asked for a general solution, weren't we? Okay, so we could say 0, 2 pi, negative 2 pi, but the general solution will be multiples of 2 pi. So that's the lesson. Now, one of the things you want to be mindful of is non-permissible values, okay? So I forgot to change, when I changed your unit, some of the typing. I do have a list of textbook questions, okay? And they're good questions. But I also have 5 multiple choice numerical response exam style questions on the following pages that I think you should do. When we learned about sum and difference identities, I did not list number 4 in the supplemental practice section. And when we did double angle identities, I didn't list number 2. That's because these all deal with equations. And you know, you can make a note here that on page 43, 4b is, the word I might even use is dirty. There's something there that you would never be expected to figure out. But some people are up for a challenge. 2i and 2j are tricky, and I would classify something here as worthy of me saying tricky if it's something that I look at and it takes me a long time to figure out, okay? So think of them as challenge problems, if you like. But I would say that if you can do textbook questions or those 5 questions in the handout, you know what's going on. Tomorrow, short quiz, say 10, 15 minutes, couple of questions, probably multiple choice numerical response, or just fill in the blank type of thing.